Welcome to week 7 of the CAD class. This is the start of a new project. Last week we finished up a 2-week project. This week we're starting another 2-week project. I've gone ahead and created a new document for this project, named it week 7 and 8. So make sure you do the same. Next week we will just be working in the same project. Okay, so I'm going to break this week session up into 2 parts like I've been doing. This first session is going to be another layout sketch that we're going to do, and then the second part will be modeling parts based on that layout sketch. So this week is probably it's maybe a little bit more advanced in the layout sketch department in some ways, but I would say that this style of doing layout sketches is probably the most important thing to get out of the layout sketch kind of skill set that we've been talking about. So I will kind of explain a little bit more once we get into it. So the project that we're going to be working on is we're going to be working on what I guess I would call a pneumatic joint. So basically it's going to be a pivoting mechanism that has 90 degrees of stroke, and it pivots up and down, and it is actuated by an air cylinder. This type of mechanism gets used all over the place on FRC robots. You will most commonly see it being used to deploy intake mechanisms, like over-the-bumper intake mechanisms, but there's also all kinds of other uses for it as well. So we're going to be designing that. We're not going to be designing any particular mechanism that it actuates. It's just going to kind of be 2 pieces of aluminum tubing that are just being actuated by an air cylinder floating in space. So this is going to be kind of like a little module that could be kind of reconfigured and used in a variety of situations. So we're gonna jump into it here. I'm going to create a sketch here on the right plane. Okay, so we are going to so the geometry of a pneumatic joint like this is relatively complicated. So we're going to use the layout sketch, and we're going to use the sketch features to figure out the exact geometry that we need, and then base all of our components on that layout sketch. So we're going to start off with just a little bit of context in terms of how we're actually going to build this thing. So I'm gonna start with the rectangle, and this rectangle represents a tube, an aluminum tube that we're viewing from the side. So I'm going to create some dimensions here. I'm just using keyboard shortcuts, so if you don't see me clicking buttons on the ribbon, that's just because I'm using keyboard shortcuts. You can click buttons or use the D key to activate dimensions if you want to. Don't know exactly how long this needs to be yet, so I'm going to leave this unconstrained. So this represents a 1x1 tube that we're going to use. So it's 1 inch tall, and then it's also going to be 1 inch deep. Not that we could see that in this orientation. The next thing we're going to do is I'm going to model another tube that is facing upright like this. Now, this is actually, I'm going to delete that and do this a little differently. I don't want this to exactly be 90 just yet. I want it to be able to move. So we're going to model this guy 1 inch wide, and like I said, we don't know how long it's going to be just yet. Okay, and then what we're going to do is we're going to have a pivot point somewhere in this region here. And this tube is going to have some brackets on it, and it's going to pivot around that point. Now, I'm not going to draw the brackets in the sketch because it doesn't matter. I'm going to represent this tube, the pivot of the tube as just kind of some very simple sketch geometry. So I want the pivot to be in the middle, like the center line of the tube. That's not necessarily super critical, but in this case, for this example, that's what we're going to do because that's pretty common. So thinking about this a little bit, there are going to be brackets on the bottom tube here as well. And then I think what we're going to do is we're actually going to put bushings in the tube, and it's going to pivot around the bushings put in this tube. Also, I realize this is vertically constrained there, which I don't want. So I should be able to move this over now. Yeah, okay. So so there's actually going to be a bushing in here. So what I'm going to do is I'm going to grab a line, and then I'm going to make sure that this line and one of these lines is parallel. And then I'm going to dimension the length of this line to be 1/2 inch. It's kind of a nice number. I might change that later. So basically what the endpoint of this line represents, this line here represents the pivot point. And I could have done this several different ways. I could have put a point there and dimensioned it off of this edge. There's a variety of ways you can do it, but this is the way that I usually do it. I'm also going to make this construction. All right, so then what I want to do is I want to dimension this from the top of the tube because this dimension is relatively irrelevant, so we just need to define it. And then I'm also going to do probably 1 inch, maybe 1/2 inch. And then I'm going to define the angle between here and here. I'm going to define it as 90, but and then the reason I'm doing it this way is because if we change the design to the where, oh, we don't want this to be straight up and down, we want this to be 80 degrees, I can just change this dimension. Whereas if I were to attach like a vertical constraint or a horizontal constraint to one of these edges, it becomes harder to change this angle. So we're going to start with 90. I think that's where we're going to stay. I think I like the idea of this tube being flush with the end of this. That just kind of looks nice and neat to put this pivot all the way out at the end. However, it doesn't actually matter. So one thing I want to bring to your attention, I'm going to draw a circle from the pivot point to the corner of this tube. I'm going to make this construction. So the thing to understand is that if I were to delete this, these corners, keep in mind that these corners sweep through kind of a, they sweep through an arc. So I could not make this a 1/2 inch because then the tube, right, the corners of the tube run into it. Even though in the 90-degree orientation, they might be okay. Here there's no interference, but as they turn, they follow this circle, right? So it's important to set this to something where this circle is outside of the the envelope of this tube basically. And then I'm just going to make this 1 inch just because I like that being up a little higher, but it doesn't really matter. Generally, I try to keep things on a 1/2 inch grid when possible. That's pretty common in FRC. However, if for space reasons, feel free to go for a tighter granularity. If you're making custom parts, you can really do whatever you want. So it's a good practice to keep everything on a 1/2 inch grid if you can, but if there's some reason why, you want this to be a little lower, you can totally go lower. Okay, so basically what's going to happen is we're going to have some brackets back here, and we're going to use a pivot mount cylinder. We're going to use a 3/4 inch bore, 4-inch stroke cylinder. I'm just defining that because that's a very, very common cylinder that gets used on a lot of things. However, you would, if this were a real robot application, you would have to do some math, maybe do some calculations, and figure out what kind of bore diameter you need on your cylinder, how much stroke length, etc., based on what you're actually trying to move. In our case, it doesn't really matter because that application is not defined. So anyways, there's going to be some bracketry back here that supports the rear pivot of the air cylinder. And then there's going to be some bracketry on this this moving tube up here that supports a clevis that's attached to the rod of the cylinder. And so then what's going to happen is the cylinder is going to extend, and this is going to move down 90 degrees, basically. 90 degrees is the stroke angle that we're looking for. So the important thing to understand here is that I don't need to sketch all of the brackets that are involved in this. I don't need to sketch the air cylinder. All I need to do is have the pivot points represented in the CAD model. So what I'm going to do here is I'm going to draw a line, and this will become obvious why this is important later. I'm going to draw a line from here to here. I'm going to make this construction. I'm going to make this parallel to that, right? And the reason I'm doing it that way is so that when I change this angle, this line's angle also changes. Then what I'm going to do is, what did I just do? Oops, there we go. I accidentally clicked. Okay. All right. I'm going to draw a perpendicular line to that. once again, I'm doing perpendicular rather than horizontal, so when I change this angle, all this updates. Okay, the other thing I'm going to do here is draw a line from here to here. Make that construction as well. This one can just be vertical because this side doesn't move. This represents the pivot point of the back of the cylinder. Now, just as a little review, I'm going to go over here to mcmaster.com and I'm going to search air cylinders. And we're going to use these double acting round body air cylinders. Stroke length of 4 inches, bore size of 3/4. We're going to do this universal mount cylinder here. So I'm going to click on the part number, click product detail, and then I can download CAD models. We're not going to do this in this video. We'll save this for next week. However, I did want to just pull up this drawing to show you guys what cylinder we're talking about. So this rod here at the front of the cylinder is going to have a clevis attached to it, and the rear pivot of the cylinder is what's going to be on this end point here. The pivot point of the clevis is what's going to be here. Now what I'm going to do is I'm going to connect these two endpoints with another line. And what this line represents is pretty important. So what this line represents is the air cylinder itself. It represents the air cylinder, in this case in the retracted state, and it represents the air cylinder with the clevis screwed on the end. So I'm gonna open up a new tab, go to another instance of McMaster, go to air cylinders. Again, click through this, and then I want 3/4 bore. Scroll down. So there's a couple of different, like we talked about in our COTS segment. There's a couple of different, types of like accessories for air cylinders. You've got these rod ends, and you also have these clevises. I typically use the clevises because they're a little bit more compact. They take up a little bit less space. Although this is like a really weird image. I've never seen this before. This is what they actually look like. But I don't know why this looks like it does. That's very strange. Anyways, we can also download a CAD model here. Now what we are actually going to need to do is actually I think we're going to go ahead and download the CAD models for these because we actually need some information from them. All of the dimensions for this guy are not actually on the sheet, I don't think. Actually, no, all the dimensions are here. Okay, never mind. Okay, so basically what we need to know is we need to know the length from the pivot of the air cylinder up to the pivot of the clevis. Now this is going to require a little bit of calculating because the dimensions that they give us are not necessarily particularly clear. So the first thing to understand is that there's a 1/2 inch of threads on the end of the air cylinder. So we know this retracted length, this 8.53 inches from the end of the rod to the back of the cylinder. Now right off the bat, the back of the cylinder to the pivot point is dimensioned as this 0.28 dimension. So I'm just going to pull up a calculator here and I'll just tell you what these dimensions are. You won't be able to see this because I'm just going to do this off to the side. So we're going to take 8.53 minus 0.28, and so that means the dimension from the front of this rod here to the pivot is 8.25, right? That's nice and fractional. That's kind of what we'd expect. So we also know that there's a 1/2 inch of threads, so that we know that when we put the air cylinder like clevis on there, it's going to thread down onto these threads. Now, the weird thing about this assembly is that this clevis does not it doesn't have to screw down a particular distance. So we can actually decide how far on to the air cylinder we want to screw the clevis. And then what we do is the clevis comes with this little nut. It's kind of just floating in space here in these renders. Excuse me. But this nut actually threads onto the air cylinder rod along with the clevis, and then you tighten the nut and the clevis together, and that keeps the clevis from spinning off of the air cylinder. So basically, we can screw this clevis on as much or as little as we want, and so we actually have some adjustment here of this length. So when we're trying to figure out what is the center to center distance between the clevis pivot and the air cylinder pivot, the truth of the matter is it's actually kind of up to us, right? There's kind of an adjustment range that we could hit. So looking at this drawing here, we get the thickness of the nut as 0.16. And so the absolute minimum value that we could see would be this nut screwed all the way onto the threads, like screwed all the way onto this through this 1/2 inch, and then the rod, the clevis itself screwed all the rest of the way onto the rod. So we can see here we've got this 0.94 and this 0.16 dimension. I mean, I can tell just by looking at these numbers, this adds up to 0.11. So if we take the dimension on the cylinder from the rod, the end of the rod to the pivot, which is 8.25, and we add 0.11 to it, or 1.1, sorry, we get 9.35. Now, the thing is we've got to account for how much we threaded onto the air cylinder. And so if we thread it on all the way, that's just 1/2 inch. So we need to subtract that 1/2 inch because screwing them together means the length is kind of decreasing, if that makes any sense. Let's do minus 0.5. That gives us 8.85. So that is the minimum center to center distance from the pivot of the air cylinder to the pivot of the clevis when the clevis and the jam nut, this little nut's called the jam nut, when the clevis and the jam nut are screwed all the way on. Now, in reality, I prefer to not screw the clevis on all the way because then that gives us a little bit of adjustment in both directions, right? We can either back the clevis off or screw the clevis in more, and that is pretty important when you're building a robot. You know, you've got some imprecision and stuff in your manufacturing, and being able to adjust the air cylinders and adjust the you know, kind of the position of this mechanism just by adjusting that clevis is very useful. So generally speaking, I will leave a 1/16 or an 1/8 of an inch on the cylinder just to of adjustment left, just to kind of be able to adjust for those manufacturing tolerance issues. I generally like to screw it on as much as I can, just because that gives you a stronger interface, but generally like to leave an 1/8 of an inch to a 1/16 of an inch, somewhere in that range. So I'm just going to make the math easy here. I'm just going to leave 0.1 inches, and so that then adds, we have a minimum center to center distance here, so leaving a 0.1 inch gap here basically increases the center to center distance. So I just need to go back to my calculator and add 0.1, and I get 8.95 is my final center to center distance. So that's what we're going to work with in CAD, that 8.95 number. And then in reality, we may have to adjust the cylinder a little bit away from that, depending on, you know, how our parts get manufactured in real life. So I'm going to attach a dimension here. I'm going to do this as 8.95. That's all well and good. Now this represents the air cylinder in the retracted state. Now we're going to take this a little bit farther. We don't know exactly where this air cylinder needs to be positioned in order to create 90 degrees of stroke. So here's what we're going to do. We're going to create some more construction lines, and these construction lines are going to represent the system that we've built here in the extended state, like when the air cylinder is extended. So I'm going to select these two guys, make these perpendicular. Now here comes the key part. This is very, very important. So what I'm going to do is I'm going to select this line, and I'm going to make them equal. Okay? And then I'm going to select this line, and I'm going to make them equal. Now, why have I done that? If it's not obvious why I have done that, it is the reason that I'm doing this is because these two lines here represent these two lines here in a different position. Like, these are representing the same part of the mechanism in two different positions. And this is a very key concept for doing layout sketches for FRC robots, where you are going to draw something in multiple different positions in order to validate your geometry. Now, what we're going to do here is we're actually going to kind of use some creative placement of some constraints and stuff to actually get the CAD software to calculate the positions of components relative to each other for us. And so that is a very useful thing, and that is one of the most important parts of doing layout sketches is figuring out ways to get the CAD software to figure out your like tough, complicated geometry for you. Okay, so we've done this. Now the thing to note here is these are not constrained, right? Like we don't actually know, oops, I accidentally created a constraint there. We don't know how long this line needs to be. We don't know how long this line needs to be. We don't know how long this line needs to be. So there's a lot of stuff that's not constrained here. But as we start to place some of these constraints down between the mechanism in two different positions, it will start to fully constrain a few items for us. Okay, so we're missing one part here. We need to draw a line from here to this point back here. Now this is going to represent the air cylinder in the extended state. Now, what is the length of this line? That can be a bit tricky. I'm actually going to do this. Actually, I'm going to do this. I'm going to back out of this. I'm going to delete this. I'm going to do this in a slightly different way. Maybe a way that would be a little more intuitive. So what I'm going to do is I'm going to create an arc from here to here. Now what we want to end up is we want to end up with a line between this point and this point that represents the air cylinder in the extended state. However, I'm going to do this in a slightly more visual way to explain it better. So I'm going to create an arc here. Now the center point of the arc is on the pivot point of the air cylinder. And I'm going to attach a line from here to here, make this construction as well. Now what this represents is the air cylinder is still in the retracted state. Now, how does the center to center distance of the air cylinder change when the cylinder is extended? Well, basically it just extends by the stroke length, right? That's kind of the definition of what the stroke length is, right? The cylinder is retracted, and then our cylinder in our case has a 4-inch stroke length, and so the cylinder gets exactly 4 inches longer when it's extended. So basically the distance between here and here needs to be 4 inches, right? So I'm going to draw a line from here to here. Now it's important that this line and this line are actually in line with each other. There's actually a slight angle here. If I put a dimension here, oops, if I select these actually, you can see the angle is 175 degrees. These are not actually in line. So it's important to either do a coincident constraint to each of these lines or do a parallel constraint. I'll do parallel because that feels a little more intuitive to me. And then the length of this line is just the stroke length of the cylinder. So I'm going to attach this dimension here, and the stroke length is 4 inches, and that's easy. Now, what you could do is what I was going to do originally, which is you could draw one line and just put a dimension here that just is equal to this dimension plus 4, right? You could do that too. It's the same difference. You don't actually need this arc, and in most cases I wouldn't do this, but I think it's kind of valuable for our kind of example here from a visual standpoint. Okay, so we've created a little bit more constraint here. Our geometry is not quite as free floating as it was before. Now we're still missing one part. We have defined what this stroke angle actually is. Let's put that dimension in here, which is the angular dimension between the two positions. Now we have defined this to be 90 degrees, which is quite a bit. Now, obviously, our geometry is very not constrained here. It's kind of freaking out on us. So once we get to a point, we can kind of start to kind of play with it a little bit more and get things into a more reasonable position here. Okay, so there's a few things that are important. So first of all, the air cylinder cannot be inside the tube, right? There would be ways to make this joint where the pivot of the air cylinder is actually inside the tube, but not easily. So we're not going to do that. We're going to find a position here where that is not an issue. Second of all, when the air cylinder is extended, the back of this tube is still here, right? You kind of remember the circle, the sweep of the corners and everything. And when the tube is laying down flat, it's going to be kind of, along in this area. The top of the tube is going to be kind of along in this area. And so when the cylinder is extended, there's actually a rod here where this line is, and we can't have this rod hit the top of the tube in the extended position. And so essentially what that means is this just needs to be long enough that there's no interference here and in this region here. Now we can kind of just eyeball it because like right now we're nowhere close, but if it starts getting close, we might need to sketch in some additional geometry. We might need to draw another rectangle or something just to represent, the tube in its other positions, and then we might need to sketch some other lines parallel to this line to represent the width of the rod and all that stuff. There might need to be some other sketching. That being said, just by looking at this now, we're nowhere close, right? This circle represents where the corners go, and in reality, we're not really worried so much about the corners. We're worried about the top face, which is quite a bit lower than this, and the rod is not very wide either. Okay, so then basically, this is about as far as we can go getting the CAD to do stuff for us. At this point, we just need to start making some decisions. So first of all, let's do a couple things that are pretty easy. This tube doesn't need to be super long. It's just going to be long enough to support this bracket. So we're going to just do, 0.5 there. And then, so there's a couple of things we can do. I think we're going to just throw a dimension on this of 12 inches, maybe 10 inches. It's kind of arbitrary how long it is, doesn't matter. And then what we're going to do here is we have a few more choices. So if you just start clicking and dragging on things, you can see what things move. So the big thing here is this thing wants to dive down inside of the tube. It's pretty important that the air cylinder is above this tube. So we're going to dimension this to be, I don't know, 0.5 inches. It's probably okay. We could go higher. Maybe go, it's just kind of a judgment call here. It doesn't really matter that much. We'll probably do that. I'm actually going to change the way that we're doing this a bit. I'm going to make this 1.5, and we'll see the reason for that later. Okay, so then basically if we click and drag on stuff, you can see our geometry, as we add all these constraints and these dimensions, when we click and drag, the geometry can move significantly less freely. So at this point, basically what's happening is there's a relationship that we've established in the CAD mathematically between the length of this line, the length of this line, and the distance from, and basically the length of this tube, right? You can see as I'm dragging, it might be a little bit hard to tell on the screen, but there's only actually 1 degree of freedom here. Everything is kind of moving in relation to each other. If I move my mouse up and down and left and right, I only see one change, right? It's kind of moving in one axis. And so understanding how many degrees of freedom you have will help you determine, it's basically how many more dimensions do you need to place, right? And so basically just by pulling on the geometry and clicking and dragging, I can tell that there's only 1 degree of freedom here. So now what I think would be nice, and at this point, let me be clear, it is completely a judgment call. I could dimension the length of this line, I could dimension the length of this line, I could dimension the angle between these two, I could dimension the distance from here to the pivot, which could be useful, and I could dimension the distance from this to here or something like that, right? All I basically just need to do is place any dimension between 2 pieces of blue geometry, or a piece of blue geometry and a piece of black geometry, and I will have completely defined in my sketch. So it's important to decide what you want to lock down based on, some design convention that you set for yourself. It doesn't actually matter. It's just, there are certain things that will be a little cleaner and certain things that will not. So one thing that might be nice to do is, because we're concerned about this rod hitting the tube, we might want to define this dimension here. And we won't want to say this will be 1.25 inches. We pick some number that's like, we know it won't hit. Now you'll notice everything turns black. Everything's fully constrained. I can't click and drag on anything. Nothing will move. I have fully defined my sketch. Now in reality, I don't actually want to do this. I don't actually care that much about what this dimension actually is. All I care about is that it just doesn't interfere. So I don't actually want to dimension that. That feels like I'm over defining things a little bit by saying that this needs to be some fractional dimension, because it doesn't actually matter. All I care about is avoiding interferences. Now, something I actually do care a little bit more about is I care about, like I mentioned earlier, trying to keep things on a 1/2 inch pitch. To me, I think it would be nice if this line was a nice fractional distance from the end of the tube, right? So if I measure from here to here, oops, it's the distance is some weird number. I would kind of like this to be fractional, and that helps if I've got a tube that has a nice even grid of holes down the side.
I can bolt a bracket or something to an even grid of holes and just keep things on this nice even increment. Now, because of the weird relationship between all of this geometry, if this distance here is some nice number, that means that this distance here will not be a nice number. That being said, this tube here is more likely to be part of like your drivetrain or something. If this is an intake pivot, this tube here is much more likely to be part of your drivetrain, or some other larger structural member. And having a nice grid of holes on a large structural member is more important than having a grid of holes on like your intake tubes or whatever. And so I am prioritizing this being on a nice pitch because of what this tube kind of represents on a robot. Now, some of that is like kind of some just knowledge and experience that I've picked up over the years, and I don't really expect you guys to, um, you know, understand what the right choice is in every situation. The thing to understand that I'm trying to teach you here is the fact that you're just kind of understanding the relationships between these different pieces of geometry. Um, Choosing exactly where to place your final dimension is largely irrelevant for you, and you will figure out over time how you like to define these sketches. So don't get hung up on, if you're doing something like this on your own, don't get hung up on exactly where to place your last dimensions and how to fully define your sketch. Just pick something. There's not really any wrong answer. It's just over time you will find a preference for certain things. So in this case, I'm going to place this dimension here, and I'm actually going to dimension it to the pivot. Not that it matters. And I'm going to make this 10 inches, nice even round number. So we've got a 1/2 inch from the end, a 10-inch center to center distance, and then we've got 1.5. So we know that this tube length is some fractional, nice 1/2 inch increment, because all the dimensions involved are in that increment. So it's 12 inches long, which is super nice. We've defined this tube to be an overall length of a nice round number. However, this line here is some weird number in length. And if you're doing custom manufactured components, that is totally okay. There's going to be a trick that we're going to use a little later that I'll show you that still allows us to put holes on this that are even spaced, but we'll get to that. Okay, so for now, I'm going to finish this sketch, and basically, the thing to understand here is that this geometry fully defines everything that we need to know about our mechanism. Like, the sketch does not need to be any more complicated than this. Now, the thing that I want to draw to your attention, and I'm actually going to create another sketch here on the right plane. And I'm not going to keep this sketch, I'm going to delete it, but I'm going to show you guys there's an important relationship here that I want you to understand. And it is important, if you are designing these kinds of joints, that you understand that the relationship between the air cylinder and two pivots is just a couple of triangles. So even though we've got this kind of like L-shaped thing here, because we care about the position along the length of the tube, and so we've broken this into, this kind of this L shape here. In reality, all this really represents is kind of like I guess you could think of it as kind of like a vector, right? Like, you've got this, it forms this right triangle, and the only thing that's actually important is the relationship between this pivot point and this pivot point. And obviously, because we're talking about 2 points, those can be connected with a line. And so the thing to understand is that this line, we've got 2 triangles. This triangle represents the system in the retracted state, and this triangle here represents the system in the extended state. And so this line here doesn't move. This line here is fixed because this represents the kind of like the structural like mounting points to the robot. This line here, or these 2 lines here, represent the pivot lever arm in 2 different positions. And the thing to understand here is this line and this line are the same length. And then in addition, the relationship between these 2 lines in terms of angle is the angle that we've defined between the retracted and extended states, right? Which is 90 degrees in our case. So this line does not change in length, but it does change in angle. This line here, these 2 lines here represent the air cylinders in the 2 states. This line here is obviously our 8.95, and this is this is that same distance except, extended out a little bit farther. Well, I'm looking at this now. Oh, I'm measuring angle, just like that. And so this is the 12.95, right? It's this other distance plus 4 inches because of the stroke. And so this line here actually changes in length as the system operates. And then one other piece of geometry that I would like to show you, an arc between there and there. This is the actual path that the endpoint follows. And so when you're looking at this geometry, it's important to understand that the whole system simplifies down to basically just two triangles, and this arc basically, and all of the dynamics of the system and everything are represented here. You don't need to draw these tubes to understand how the system works. So I know that might be a little bit advanced, and it might take a little bit to get to the point where that is understood and becomes, I guess, second nature, or becomes like something you kind of understand at a low level. However, it's important just to understand that this geometry is kind of floating out there in space when you're working on a pivot like this, and it's important to understand what those relationships are. So if you don't get it right away, don't worry about it. During the build season and everything, as you guys progress through these projects, RoboCharger students, I'll be there to work with you guys and help you guys through this. You only need to do these kinds of layout sketches a few times in a season. It's not like you're doing this every time you're sitting down to CAD something. Working out this core geometry is a relatively large, momentous occasion, I guess, in the CAD design process. And so, you will have some help, and you won't be on your own when we're doing this. I'm actually going to exit out of this sketch because I don't actually need any of that. We're going to wrap it up here. This is all for the layout sketch. In the next video, we're going to actually design the parts that are associated with this assembly. So I will see you guys in the next video.